So to continue with the patterns that we noticed with our example, the mean of the sampling distribution of the sample means always equaled the mean of the population where the samples came from. The standard deviation seemed to be getting smaller as my sample size increased, and the population was normal and the sampling distributions all looked normal. And yes, we did see these patterns, and in fact they're always true as stated. So we actually see this relationship. If a simple random sample of size n is drawn from any large population, then the sampling distribution of their sample means will always equal the mean of the population. And the symbol for the sampling distribution of the sample mean, it's mu sub x bar. And that will always equal the mean of the population. The standard deviation, called the standard error of our sampling distribution of the sample mean for samples of size n, its symbol is sigma sub x bar. That will always equal sigma divided by the square root of n. As the sample size increases, the standard error of our sample mean gets smaller. That is, we have less variability in there. As our sample size increases, our guess gets better. And we also note that if the population is normally distributed, then the sampling distribution is normally distributed. And that gives us a full description of our distribution. And we, even now that it's normally distributed, could use our standard normal table to find probabilities. Description of the sampling distribution. If you repeated taking the simple random sample of size n from a population and calculate the sample mean for each of the samples, the distribution of this accumulation of sample means is what we call the sampling distribution of the sample mean. And remember, the sampling distribution of the sample mean does not necessarily look like the population distribution. That only happens when our population is normal. So let's look at an example when we don't have a population that's normal. So what would happen then? Well, we know that all sampling distributions means will be the mean of the population, and the standard errors will be sigma divided by the square root of n. But what about the shape? How would we be able to find probabilities? So let's look at this population that is right skewed with a population mean of 2.56. We're going to look at a sampling distribution of the sample mean for samples of size 10. Now with this, the mean is 2.56, and the standard error would be whatever the standard deviation is divided by the square root of 10. But we can't get the probability for this because it's neither the original population nor is it anything else. It's something that's becoming more symmetric, that's for sure, but it's still right skewed, but we don't know what that distribution is. Now let's look at what would happen if I took samples of size 40 and 160. The mean will be 2.56. The standard error for the sampling distribution of the sample mean for samples of size 40 would be the population mean divided by the square root of 40. But now look at the shape. That is one symmetric distribution, and what we find is that's actually approximately normally distributed. And the same is true for the sample of size 160. It has a shape that is approximately normally distributed. In fact, it looks very normally distributed. So we might, if it is true that these are normally distributed, we'd be able to use the normal distribution also to find these probabilities. And that would be pretty significant because that means that any distribution, if I take sample sizes large enough, I could use the normal distribution to find probabilities. And we know the mean of these distributions will always equal the mean of the population, and we even know the standard deviation, that standard error, the standard deviation of the population divided by the square root of n. So that would mean if I can estimate the mean of a sampling distribution, I could estimate the mean of the population. And that's where the power of a sampling distribution will lie. But for right now, we're going to work opposite. We're going to say we know the population and work within the sampling distribution to get us used to how to use it and some of its properties. So if our population has a normal distribution, then we know our sampling distribution of the sample mean will be normally distributed for any sample size, for samples of any size. However, if the population doesn't have a normal distribution, like the example we just saw, what can we say about the shape of that sampling distribution? Well, we saw that if n gets large, it starts to look normally distributed. And in fact, there's a central limit theorem that has been proven. And we find that Regardless of the shape of the population distribution, the sampling distribution of the sample mean becomes approximately normal as the sample size n increases. So most population distributions aren't normal. So what is the shape of the sampling distribution of the sample mean when the population distribution isn't normal? Well, if we've got small sample sizes, we won't know what it is. But by the central limit theorem, if the sample size gets large enough, it becomes approximately normal. So there is a period of no man's land from a small n to these n's large enough that we wouldn't be able to get probabilities, but if n is large enough, we can use the normal distribution to find probabilities. And in our class, n for n greater than or equal to 30, we can evoke the central limit theorem. So the central limit theorem would say that all sampling distributions become approximately normal as n is, in our class we're going to say n greater than or equal to 30. So we would say our sampling distribution has a mean equal to the mean of the population and a standard error equaling sigma divided by the standard deviation, that is, divided by the square root of the sample size. And we'll use n greater than or equal to 30 as the convention in our class. It's not necessarily true, but in real life there could be, you might have to need a larger sample size or a smaller one, but in our class we'll always say 30 or more, we're able to evoke the central limit theorem. So we can take from our law of large numbers and our sampling distribution some notions or some ideas. The distribution of measurements in a sample looks like the distribution in the parent population when n is large, not necessarily like the normal distribution. The sampling distribution of the sample mean looks like a normal curve as our sample size increases, even though the parent population isn't normal. As the sample size increases, the sample mean gets closer to the population mean. That is, the difference between the sample mean and the population mean tends to become smaller, approaches zero, by the law of large numbers. Therefore, the spread of the histograms for the sampling distribution of the sample mean is getting smaller for larger sample sizes. Our guess is better, so the variation is less. So, there's a couple of problems that you will be doing in lab this week that will help you to solidify your understanding of the central limit theorem and using the sampling distribution of the sample mean. So the sample mean is a random variable with a probability distribution. We call it the sampling distribution. The mean of the sampling distribution will always be the mean of the population, and the standard deviation, called the standard error for our sampling distribution, will equal the population standard deviation divided by the square root of n. Shape of the sampling distribution, well, if our sample size n is sufficiently large, 30 or more, then the distribution is approximately normally distributed, no matter what the population distribution was. And if our population was normally distributed, then it doesn't even matter what n is. All sampling distributions will be normally distributed. Now we're going to take a quick look at the sampling distribution of the sample proportion. Now, remembering the binomial that we just learned, what that was is it has a fixed number of trials, only two outcomes, success or failure, and trials are independent, and the probability of a success is p, and it's the same for each trial, where our random variable is the count of successes in a binomial situation, so the number of successes out of the n trial. If we take that, we know the values will be between 0 and n. This will help us when we're starting to talk about proportion, because with the binomial, we know the mean of a binomial is n times p, and the standard deviation is the square root of n times p times 1 minus p. But something we didn't talk about is that as n gets very, very large, we can actually approximate our binomial distribution using the standard normal distribution. And the rule of thumb is if n times p and n times 1 minus p of our binomial, if both of those are greater than or equal to 10, then we can use the normal approximation for our binomial and get very good estimations. And this is where it's going to come in to help us with sample proportion. Because the sample proportion is the count of successes in a sample divided by the sample size. So it's our binomial divided by the size of the sample. So if we remember that the mean of the binomial is n times p and the standard deviation is the square root of n times p times 1 minus p, If we divide that by the sample size, then we're going to get the mean and the standard error for our sampling distribution of the sample proportion. So if we just looked at an example of a proportion problem, a polling company polls 1,200 people to see if they supported a certain issue. We know that 408 of them did support it. Then X is the number of people who supported the issue. That's that binomial random variable. But we divide that by our sample size, and now we have our sampling, our proportion, our sample proportion, and we can determine what that is. Now, because the values of a sample proportion vary from sample to sample, once again we have that random variable. So what is the mean of that sample proportion? What is the standard deviation of the sample proportion? What is the sampling distribution of the sample proportion? And can we apply something like the central limit theorem so that to these with the normal distribution? And the answer to this is yes. Because the values of a sample proportion vary from sample to sample, it becomes a random variable, and we can create the sampling distribution of the sample proportion for samples of size n. What would the mean of these be? Well, the mean will just land on p, just like our mean of our... What's the standard deviation of the sample proportion? Well, that's our standard error, and that's going to be the square root of p times 1 minus p over n. We take the square root of that quotient. So now we have a full description of our sampling distribution of the sample proportion. If those conditions are met, that n times p and n times 1 minus p are both greater than or equal to 10, then we can approximate our sample proportion just like our binomial with the normal distribution, where the mean of it will be p and the standard error will be the square root of the quotient p times 1 minus p divided by n. Some of the conditions: independence. The individual samples must be independent of one another. Samples were obtained from a simple random sample or a randomized experiment. The sample size should be no more than 10% of the population. We will always, in our class, assume that to be true. And the success or failure condition, n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10 has to be true. Both of those quantities, n times p and n times 1 minus p, both have to be greater than or equal to 10. So in your discussion, you will be going over this problem with the TA to look at how sampling distributions of the sample proportion behave and how you would use them. So between these two videos, you learned about the population distribution versus the sampling distribution, the mean and standard deviation of the sample mean, sample distribution of the sample mean, central limit theorem, and its importance to both the sampling distribution of the sample mean and the sampling distribution of the sample proportion. Thank you.